This video provides an introduction to related rates using a few simple geometric examples. When two quantities are related by an equation, if one quantity is a function of time, then so is the other. And in our example, suppose an ice cube is geometrically an actual cube with a side of length 3 at a particular instant. So let me draw a picture. My ice cube is some sort of cube. So it has these dimensions, and if I think about the sides and call it S, I have all of the three dimensions have the same side, but this cube also has a volume. And so if my side is changing, so is the volume. And that's the idea of related rates. A problem is a related rates problem when we use the rate of change of one quantity to find the rate of change of another. So now in our problem that is proposed, we're saying that at a particular instant, we know that our side length is 3 centimeters. Now that does not mean that it's sitting constantly at 3 centimeters, but at the instant of observation it is 3 centimeters. What else do we know? If the length of the side is decreasing at a rate of 1 millimeter per minute, so there's some more information, we have a rate, which means a derivative, 1 millimeter per minute. So this is telling me that I have a rate of change, and that represents the rate of change of side length with respect to time. Because it's decreasing, I'm going a negative rate of change, and 1 millimeter is a tenth of a centimeter, so 0.1 centimeters per minute. We want to know what is the rate of change of volume. The rate of change is given by a derivative, and so our question is, what is the rate of change of volume? In order to answer this question, we start by creating an equation for the variables. Our volume can be found as the cube of our side length, and this is our related variables equation. From this, we create a related rates equation. A related rates equation is found by taking derivatives, just like we did with implicit differentiation, of both sides of our equation, except that our independent variable is time instead of one of our quantities of observation. Our related rates equation says that the rate of change of volume, dV dt, is the same as the derivative of s cubed with respect to time, which is 3s squared ds dt using the chain rule. In our problem, we've identified the value for s and for the rate of change of s, and we can use those quantities in our formula to be able to determine the rate of change of our volume. So for this problem, we are given 3 times s squared, which is 3 centimeters squared, times ds dt, which is negative 0.1 centimeter per minute, which gives me negative 2.7 cubic centimeters per minute. And so this is the rate of change of my volume. For my second related rates example, I want to think about a raindrop. As a raindrop falls, it evaporates. Well, unless it's really humid, then it'll grow things. But I was in Arizona, and there it evaporates. And so as my raindrop is falling, it's losing water. So for this problem, we have at a particular instant that its radius is 3 millimeters, and at that same instant, we have a rate of change that water evaporates at 5 cubic millimeters per second. So let's summarize that. We'll draw a picture. So here's a picture of a sphere, and my radius is 3 millimeters. Again, this is at an instant. The raindrop is actually shrinking, But at this instant, the radius is 3 millimeters, and now I need to determine what this rate of change is. And the key is that as I'm looking at this quantity, millimeters cubed tells me that that's a volume. And so I have a rate of change of volume for the information that I'm given. So I'm also told at my instant that the rate of change of volume with respect to time, it's decreasing, so it's -5. And that's in cubic millimeters per second. Okay, so the key quantities in my problem, this is an important step, we identify our variables. The quantities of interest are V for our volume and R for our radius. And the first step for any of these related rates problems is to come up with an equation relating those variables. For us, we're told that the raindrop is a sphere, so my volume is the volume of a sphere. I look that up and I get 4/3 pi r cubed. And it's important to recognize that pi is a number. So this is a constant. From our equation, we create our related rates equation. And the related rates equation is found by taking a derivative with respect to time of both sides of our equation for our related quantities. Derivative with respect to time of volume equals the derivative with respect to time of 4/3 times pi r cubed, which tells me that the rate of change of volume, dV dt, is the same as, well, we have a constant multiple. So 4/3 pi is a constant. It factors through the derivative, so 4/3 pi. And then I take a derivative of r cubed, which is 3r squared because of the chain rule, dr dt, rate of change of my radius. And the key is we were given that the volume rate of change was -5 cubic millimeters per second. We get 4/3 pi times 3. My radius, I also know, is 3 millimeters, so I square 3 millimeters squared, and I'm left with dr dt is an unknown. I don't know the rate of change of my radius. But I only have one unknown now. I can solve for the rate of change. Let's see, the 3, what can we simplify? 3's cancel, and I get -5 equals 36, because that's 4 times 9, 36 pi dr dt. Divide both sides by 36 pi, and I find that the rate of change of my radius for my raindrop is -5 over 36 pi. And the units are millimeters per second. How do I know that? Well, my volume has units of millimeters cubed per second. And if I thought about the units of my quantities, 3r squared has units of millimeters squared, meaning that my dr dt has to be millimeters per second so that the units balance. And this is my rate of change of my radius. I could use a calculator. Pi has the value of 3.14159 approximately, and I could get a decimal value. But this is the exact formula for the rate of change of radius.